Welcome everyone to our next N3AS seminar of this spring semester. And today we're very happy to have one of our N3AS alumni, Evan Grohs from North Carolina State University, to tell us about Dirac neutrinos and distortions to the cosmic neutrino background. Please go ahead, Evan.
Well, thank you, Evan, for the introduction. This is going to be a talk on two projects that I'm currently working on. This first one on Dirac neutrinos and anomalous magnetic moments, and the second one on trying to characterize distortions to the cosmic neutrino background using BBN abundances and other cosmological parameters. I'd like to keep this pretty light, and so I'm happy to take questions during the talk. I can't see the chat, so please just interrupt or alert Evan or Anupam. And I'm happy to pause so that I can address any confusions or answer any other questions. So the first thing I will talk about are using anomalous magnetic moments to populate the opposite chirality Dirac neutrino states in the early universe, leading to extra energy density and subsequent ramifications on cosmological observables and parameters. So I'll discuss briefly what I mean, by Dirac as compared to Majorana. Again, kind of in the context of cosmology. I'll talk about magnetic moments for neutrinos, how this leads to extra populated states if they're anomalously large. From there, I will discuss just briefly some of the ramifications on later time cosmology during neutrino-free streaming in the later to current universe. And then from there, I'm going to segue just talking about relativistic energy density and how that might be able to be used in the future with abundances to constrain distortions to the cosmic neutrino background. So that'll be the second part of my talk. Depending on how much time we have, we might go a little quickly through this, but I would like to at least show you some of what's in progress here and how we're using something that we call the generalized entropy approach, which is almost like a generalization of the grand canonical ensemble from statistical mechanics in order to characterize the out of equilibrium neutrino distributions. And we're able to do this just using three parameters, which was a little bit of a surprise for us, but there's some qualifications to that. And finally, I'm going to show the abundance responses to neutrino perturbations, both time independent and time dependent. So perturb the neutrino distributions and see how that changes the abundances. But first, let's begin with magnetic moments. So I have this cartoon on the left-hand side of the slide. A little bit complicated, a little bit messy here, but this is what I'm trying to go after. Let's say that we have these four neutrino states here. So left-handed, right-handed, or left chiral, right chiral. Neutrinos and antineutrinos. Now, these two states on the left-handed neutrino and the right-handed antineutrino, I'm calling those active, right? Because they actively participate in weak interactions. Conversely, these ones more in the middle of the screen, right-handed neutrino, left-handed antineutrino, I'm calling those inactive, right? Because they're not going to be participating in the weak interaction. Now, if neutrinos are Dirac, all four of these states are distinct from one another and possible. Now, if neutrinos are Majorana, on the other hand, then there is no difference between a neutrino and an antineutrino, and so left-handed is the same, for neutrino, antineutrino, and similarly with the right-handed states. Now, I'm not an expert at all in neutrino experiments, but from my limited reading of the background, it seems like it's very difficult to tell the difference between Majorana and Dirac character. If neutrinoless double beta decay sees a signal, that is a smoking gun for Majorana neutrinos. Neutrinos have to be Majorana if you see a signal. There's also other ideas on trying to find, determine the difference between Majorana and Dirac. I point to this paper by Baja, Andre de Govea, and Boris Kaiser, which uses sterile neutrinos to try and find the difference between Majorana and Dirac. Regardless of whether neutrinos are Majorana or Dirac, they possess non-zero magnetic moments in the standard model. This cartoon that you see on the left is a diagram of the magnetic moment term. And what you can see here, right, is that you have an incoming state of a left-handed neutrino, this N sub r, think of that as a right-handed neutrino in the outgoing state, and also a photon. Now, the magnetic moment, we're going to call this kappa. It can be different. The IJ represent flavor or mass eigenstate, but in this case, I'm thinking of kind of a flavor eigenstate. And we'll write this as equal to the Bohr magneton multiplied by this magnetic moment strength. Now, in the standard model, this diagram is very small. And so you only expect, these magnetic moment strengths to be on order, 10 to the minus 19, 10 to the minus 20 Bohr magnetons, which is much smaller than what's currently probed. So if you ever see some kind of evidence of a neutrino magnetic moment, then there must be some other diagram that's contributing to that. And any kind of anomalous magnetic moment would be evidence of beyond standard model physics. So this is what's motivating us to look at this problem in cosmology. So how to begin? We're going to pick a model. We're going to drop all kind of flavor or mass eigenstate dependence. So we'll just look at one magnetic moment, which is the same for all neutrinos. This vertex function that you see over here on the left from this seminal paper by Morgan shows, the coupling of the neutrino to the electromagnetic current through a tensor operator. So we'll take this tensor operator, scale it by our magnetic moment strength, calculate amplitudes, differential cross sections, total cross sections, thermally averaged cross sections, and finally get a scattering rate, typical for the conditions of the early universe. The two rates that we look at are elastic scattering of neutrinos on charged leptons and the CP conjugate of this. And in addition, annihilation with a left-handed state and a right-handed state coming together to form a charged particle pair. Now, we're going to do these calculations in the early universe. And so as a result, these interactions are going to occur in a plasma full of standard model particles, and these particles obviously have charges to them. So we adopt a static screening prescription and use the Debye screening length, right, to come up with this effective photon mass, right, that you see over here on the left-hand side of the screen. We're going to use this to modify the virtual photon propagator, all right, that you see over here on the on this slide, in order to calculate the amplitudes and eventually the rates. So as an example for neutrino fermion elastic scattering, you get this kind of a result here. And we don't need to go in through all the details of what this means. You can see there's an m gamma squared in these terms. And most importantly, if you just look at the prefactor, you see the mu squared for the scaling with the magnetic moment strength. You see alpha squared for the fine structure constant. The plot over here on the right shows this effective mass scaled by temperature as a function of temperature in the early universe. So this is from a TeV on the left down to 10 MeV. And you can see that we do use this quantity, although it's fairly constant, right, over this huge temperature span. The differences that you see, the increases are when more particles are coming into the plasma, or conversely, if you start at high temperature and go to low temperature, these are events of when particles are annihilating raising the plasma temperature while conserving the entropy. So what we will assume for the purposes of this work, right, is that we will take all of the processes of elastic scattering and annihilation on each charged particle species. We'll sum those together to get a total neutrino scattering rate, which we'll call gamma nu. This plot on the left, the blue line that you see here, okay, is that total scattering rate for a magnetic moment strength of 10 to the minus 13. Now, plotted in comparison to that, this dashed green line, this is the Hubble expansion rate. So at high temperatures, when the scattering rate is larger than the Hubble expansion rate, we're going to say that those inactive Dirac neutrino states are fully populated. Okay, so they're thermally populated, same temperature as the rest of the standard model plasma. Once the scattering rates fall below the Hubble expansion rate, so in this case around 2 times 10 to the 5 MeV or so, we're going to say that's instantaneously decoupled. And so now the inactive Dirac states will just simply free stream, okay, as the universe expands. And as a result of the particle pairs annihilating in the standard model, that will dilute the energy density of those Dirac states, and they'll contribute less and less to the total radiation energy density, but nonetheless, they will still be there. The plot on the right shows the magnetic moment strength as a function of this decoupling temperature. Now, I should just note here, right, that we are going to these TeV temperatures, which are probably above the electroweak transition. This is an area, an active area of research in cosmology. And so we always just assume that we always have the standard model, and we can always calculate these scattering rates, you know, based off of standard model physics. That's probably not the case. So you should take this line as it goes to TeV as an extrapolation, right? And not as a prediction.
Can I stop you for 1 second? It looks like we have a few questions first.
Yeah, absolutely.
From Susan.
Go ahead, Susan.
Oh, thank you very much. I just want to be sure. That looks like a very big magnetic moment to me. I'm full of a significant direct constraints from reactors.
Yeah, I will talk about that later.
Magnetic moments, and then there's all work from Misha Voloshin in the sun, and also solar physics or solar neutrino physics constraining transition magnetic moments also. And so I'm hoping you'll also contrast transition magnetic moments from Dirac ones.
I'll talk about that a little bit later on, indeed.
Thank you.
You're welcome.
Great. And then we had, looks like another question from Julian.
Yes, just I might be confused about the reactions you put, because if you have, let's say, vanishing magnetic moment, the decoupling temperature seems to be, I mean, if you don't have if you don't take into account the magnetic moment, you have a decoupling temperature of 1 megaelectron-volt. So why is it not the case here?
These are for the inactive Dirac states that are decoupling. Indeed, the active neutrinos stay coupled until MeV temperatures based off of the weak interaction.
Okay, that's the inactive. Okay, sorry.
No problem. So calculating the total scattering rate, comparing it to the Hubble expansion rate, we'll get an instantaneous epoch of decoupling, right? From there, we'll find that temperature and a quantity that's called G*S, which is an effective entropic statistic encoding the degrees of freedom in the plasma entropy. And using that statistic, we can calculate, okay, what the change in the radiation energy density is. This is commonly used through a parameter, a cosmological parameter called N effective, for the effective number of degrees of freedom. And it's given in terms of G*S by this formula over here. Notice that there's a factor of 3 in front of this. So if you have a Weil fermion, just some kind of, massless neutral fermion, all right, you would just get this expression here in parentheses, raised to the 4/3 power. But because we're doing Dirac neutrinos, there are 3 eigenstates that you have to account for. And so you pick up this enhancement of 3. And so this plot that you see here on the left, delta N effective versus the magnetic moment strength, right? You can see as a function of mu what the change in delta N effective is. And to Julian's point previously, if you have a large magnetic moment, delta N effective is going to be equal to 3. And so basically that means that the inactive neutrinos would be decoupling simultaneously, okay, with the active neutrinos, around a temperature of an MeV or so. But as you lower the magnetic moment and you push decoupling to higher and higher temperatures, right, eventually going beyond the quark hadron transition, all right, you can put constraints on lower and lower magnetic moments. We're not the only people to look at this physics. This is interesting physics, because of this factor of 3 enhancement here. And so I'd also point you to these other preprints and the figures in them that are very similar to what we have up here, if you're interested in this. So zooming in on that N effective plot and just using a smaller range in the magnetic moment strength, we have this plot here on the left, right? So the blue line is the same as the blue line in the previous plot. And for comparison, I've drawn 1 sigma error bars from Planck on delta N effective, and also a projected 1 sigma error bar from CMB stage 4. And you can see here at 1 sigma or so, the decoupling, the magnetic moment, all right, that would not, put any kind of tension with the Planck data, above 1 sigma is a few times 10 to the minus 12. We'll call it 5 times 10 to the minus 12. But very importantly here, future, generation CMB experiments are going to push this down to, perhaps sub 0.05, maybe the 0.03 level or so. Now, even if you don't really care about this magnetic moment kind of business, just take away from this the fact that if you have Dirac neutrinos and they are in thermal contact with the standard model right below the electroweak transition, you have to see that, okay, in delta N effective at nearly a 4 sigma level. If you don't see that, that puts strong constraints on whatever physics that could be in operation with those Dirac neutrinos. Now, in addition to the energy density, there are the primordial abundances that are derived from BBN. I'm not going to talk a lot about BBN because that'll be more in the second part of this talk. But as you can see from these plots, they follow the exact same shape as the delta N effective plot. And that's because the only thing that's changing here in BBN is the extra radiation energy density, which changes weak and nuclear freeze out during the time when the light elements are synthesized. And so again, you can put a similar constraint on the magnetic moment strength using the abundances, but the tightest constraint is actually just from radiation energy density as measured in CMB power spectra. Now, one thing that I thought was a pretty interesting thing is that these are neutrinos. We've talked about, the fact that neutrinos are, the masses of neutrinos are very important, and it's what makes these things Dirac fermions or Majorana fermions as compared to Weil fermions. In addition, though, right, even though the masses are small, cosmology, especially the coming in the coming decade, is going to become very sensitive to the extra energy density, all right, at late times given from the neutrino rest mass, all right. And so since we are putting in these Dirac, these inactive Dirac states, CPT invariance tells us that they have to have identical masses to those active mass eigenstates. And so we can, at least investigate what will happen in later time cosmology. Now, in order to do this, we need to introduce the sum of the light neutrino masses cosmological parameter. So this basically is just a parameter that's telling you how much energy density there is in matter in the neutrino sector. Now, the way we're going to do this investigation, and there's other ways you can certainly do this, but for the purposes of this exploratory work, we looked at the free streaming scale, this KFS, which is related to the expansion rate and the scale factor, and then this thing that's called the thermal velocity. And what we did here is that instead of just calculating the thermal velocity, with an ensemble average over the active states, we weighted that also with the inactive states. And so we had a different thermal velocity and hence got a different free streaming scale. So this plot here on the left shows the free streaming scale as a function of the scale factor in an expanding universe. This is for a calculation where the magnetic moment strength is about 10 to the minus 14. Okay, the blue curve is for a neutrino mass sum of 60.6 millielectron volts in the normal ordering, and the green curve you see here is just if you were to take all the neutrino masses to be 0, and so then you would just have neutrinos moving, free streaming at the speed of light at all times. In addition, looking over here on the right, this is the free streaming scale measured at the current epoch for a neutrino mass sum of 60.6 millielectron volts, and shows the dependence on mu. And so you can see that there's only a few percent kind of dependence on here. And the free streaming scale is not a direct cosmological parameter. It's important, all right, when you're trying to do large scale structure calculations, and it would come into play in the cosmological CMB measuring of the lensing power spectrum. All right, so that's important to know where the neutrinos are, right? How large of the objects, right, they can encompass, given how far that they can move. So it's an interesting thing to look at, but it would need more work in terms of actually trying to get, any kind of parameter estimations or constraints out of this. Now, again, go ahead. Okay, if there's no other questions, addressing Susan's past question, here is a table taken from our preprint on some of the terrestrial experiments and astrophysical analyses, and then also the cosmological analyses. So we put a limit based off of the 1 sigma and effective uncertainty from Planck of 5 times 10 to the minus 12. Now, as Susan was mentioning, if you're doing transition magnetic moments, which has to be the case for Majorana neutrinos, we worked on this a few years ago and only put limits on order of 10 to the minus 10. And that's because the neutrinos have to decouple during BBN, all right, because there's no extra energy density from a Majorana from the Majorana states, all right, until they start to decouple from the electrons and positrons. The best limit that you see on this plot in this table is from red giant stars, the cooling of red giant stars, which is just at 10 to the minus 12. And the best limit that you have from terrestrial kind of experiments is the dark matter direct detection using xenon n-ton data, which is a pretty recent analysis. But just keep in mind, right, that we're still orders of magnitude away from like a standard model kind of range. And in addition, from CMB stage 4, this is going to push the Dirac cosmology limit, down into the 10 to the minus 13 kind of a range. Now, as a segue, what I want to talk to you about is what happens if, future CMB experiments see something that's in N effective, that's statistically different than the standard model prediction of 3.04 or so, right? Now, I think there's probably a couple of things that this could be. First and foremost, I think you have to at least consider the possibility that maybe there's some inaccuracy in the numerical calculation, some unaccounted for systematic effect. I think this is extremely unlikely, given the fact that there are multiple groups, okay, across the world who have worked on this, and they all agree, on this number to, basically 10 to the minus 3 or so. If you see something that N effective is larger than this number, right, it's possible, right, that there could be some thermal relic, some kind of scalar, maybe some wild fermion, right, not a neutrino per se, but something that could be in there that's giving you a little bit extra energy density. Now, if it is some kind of neutrino contributions, well, there's a couple of different ways it could come in. One way would be through a lepton asymmetry. Okay, if there's more neutrinos than antineutrinos or vice versa, you have a change in N effective, which is related to the lepton number for small values of the lepton number like this. Now, I said, stage 4 is looking at maybe 0.03, okay, at 1 sigma. And so that would be a lepton number of 0.1. And a lepton number of 0.1 is actually fairly large, and BBN by itself, specifically the helium abundance, is pretty sensitive to this. And so you would probably see something in helium, all right, before you would see it in the CMB. Nonetheless, it's something to keep in mind. Now, in addition, right, besides the active neutrinos, if there are these inactive Dirac states out there, they could be populated. I gave one example of anomalous magnetic moments, but perhaps, there are other processes which may populate those states. In addition, there could be just sterile states, slightly heavier masses, inspired by the short baseline reactor kind of anomalies. That's a whole different talk in itself. So let's move on from there. Now, the last thing that I think could be kind of interesting here, all right, is the fact that maybe you don't have standard BBN, all right? And so the neutrino distributions perhaps don't look like thermal distributions. This is a difficult thing to do because deuterium is measured to high precision and agrees exquisitely well with the standard BBN prediction. So if you have some kind of neutrino spectral distortions, all right, that are giving you extra energy density, all right, you have to make sure you understand what they're doing, right, with the abundances and specifically with deuterium. And that's the inspiration for this future work that I'm working on with Matt Wilson, Dick Bond, George Fuller, and Joel Myers. And in this approach, what we were trying to do is model this rich physics, all right, that you see over here on this plot on the right, using something that's called the generalized entropy approach. So let me just briefly explain what this plot is, and then I'll tell you about some of our preliminary results. So this top panel that you see here, this is showing you something about neutrino decoupling, how the neutrinos decouple from the electrons and positrons. The vertical axis is this epsilon quantity, which is like an energy, and the horizontal axis is a decreasing temperature quantity. So time is moving from left to right. Now, the dark regions that you see here, all right, this is basically, I don't know if static is the right word, but the neutrino distributions aren't changing, right, in these regions here. Okay, the kinematic region, okay, where the neutrinos are going out of equilibrium is this colored region right here. All right, now below this, I have plotted the neutron to proton ratio, okay, as a function of the co-moving temperature parameter, TCM. The solid line here is an actual calculation, calculating the neutron to proton rates and seeing how that changes this ratio, whereas the dashed line is what you would assume from weak equilibrium if the neutron to proton rates were fast enough to keep this ratio in equilibrium. This is happening very similarly, right, to when neutrino decoupling is. And in addition, the elements, these light elements, are being synthesized, right, also during this same time. And this plot down here shows the mass fraction as a function of TCM. The solid lines are from an actual nuclear reaction network calculation, whereas the dashed lines you see here are assuming nuclear statistical equilibrium. So you can see kind of at different times, some of the lighter abundances, some of the lighter mass abundances, deviating from NSE. The same thing happens with, the lithium and the beryllium isotopes too, but I just didn't draw that on this because they're never in NSE for this mass fraction range and this temperature range that I have plotted. So there's a very rich physics at play here, all right, in the early universe. And in general, what people have done, right, is to describe the neutrinos, just using the grand canonical ensemble that everybody's familiar with from from statistical mechanics. Excuse me. So in this case, right, you basically just take, an entropy function and you extremize that, assuming that all the particles can be represented in single particle states. And you get an expression that looks like the Fermi-Dirac distribution, okay, where alpha 0 and alpha 1 that I've defined here are these Lagrange multipliers, right, in this formalism. Now, here's what we're trying to do in the generalized entropy approach. We're not trying to just look, right, at single particle states. We're trying to be general here and look at multi-particle states. And instead of using an entropy function, we use something that's called an entropy content operator, right, to find these distributions. And I have written here, what this distribution looks like once you reduce it to a single body function. And I know it looks completely trivial compared to what I wrote up above for the grand canonical ensemble, but it's important to note that alpha here is not just going to be the 2 parameters from the grand canonical ensemble. It could be many more. It could have, quantum dependence in it. And what we want to use, right, this generalized entropy approach for is to describe BSM models. So if you see some kind of change, right, in the abundances, in N effective, maybe even in like free streaming, okay, at later times, you could kind of piece together what a BSM model might be able to do that and what the neutrino spectral distortions would be as a result. That's the goal. The first step is obviously just to use, okay, this approach in standard BBN so that we can understand just the small responses, right, to the neutrino distribution functions. So as a first step, what we did, right, is we looked at just the decoupling. All right, so this is neutrino decoupling from electrons and positrons, the electromagnetic plasma. And we did this using our code burst, all right, which did the out of equilibrium neutrino transport. That's these solid lines that you see on this plot here on the right. So the vertical axis just gives you a difference from equilibrium. The dashed line, the dashed black line that you see at 0, that's Fermi-Dirac equilibrium, assuming that neutrinos just free stream. Okay, these solid lines with different colors, right, are showing what the distribution looks like, the deviation from equilibrium at subsequently later and later times, earlier temperatures, with the teal line being the final freeze out neutrino distributions. Okay, now the dashed dot lines that you see here that kind of overlap the solid lines, okay, that's the result of a 3-parameter fit. All right, so instead of just using the 2 parameters of the grand canonical ensemble, we expanded it to use 3 parameters like you see here. Now, very importantly, alpha 0, alpha 1, alpha 2, they're functions of time. Okay, they change with TCM. So it is 3 parameters, but it's a 3-parameter fit in time. Okay, this is not at this point, this is not a predictive kind of a process, right? This is just a fitting procedure. But what's important to note is that compared to the 2-parameter fit of the grand canonical ensemble, this is much improved. If you just use alpha 0 and alpha 1, all right, the deviations from equilibrium, the deviations from the results from burst are much larger than what you see here. So this is something that we thought was interesting, the fact that you only need, okay, 1 additional parameter to describe this kind of physics. Now, moving on, kind of changing gears here, we looked at also the responses of the abundances to perturbations in the neutrino distributions. So what this experiment is what we would start with Fermi-Dirac distributions. We didn't use any kind of energy transport, right? We're just doing the changes in the neutron to proton rates and the associated changes to the primordial abundances. We would perturb a single energy bin of the electron neutrinos, right, to see the mass fraction change in the abundances. For example, over here on the right, this is the helium response as a function of changing the energy density in each bin. Now, if you change the energy density, you're changing obviously the expansion rate. So we compensated for that with reducing the energy in like a mu or a tau of neutrino distribution, so that we would have the same energy density. And in addition, when you change nu-e, you're also introducing CP asymmetry. So we would change nu-e bar, okay, in accordance with nu-e, so that we always had the same lepton symmetry. Now, it's not really important what the values are that you see here. What's important is just to look at the scaling and see that this is a linear response, right? So as you change the delta n epsilon, right, by the same amount, you get an equivalent change. a proportional change right here. You can see around epsilon or of 6 or so, you actually flip the signs. And so you get, an increase in helium as compared to a decrease in helium for delta N epsilon greater than 0. So the last thing that I'm going to talk to you about, right, is doing the exact same experiment that I mentioned on the previous slide, but now perturbing those energy bins in both in energy and at a specific time, or TCM. So if you can see this on your screen, hopefully, there's a grid, this light blue grid. And what we're doing is that in each one of these grids will perturb, okay, the neutrino distributions. Epsilon is on the vertical axis and TCM is on the horizontal axis. And so the blue and the red regions that you see here, this is the response of the neutron to proton ratio, right? So instead of just looking at helium, it's just the neutron to proton ratio, right? For these responses here, right? In addition, I've also mapped on these contours from the differential visibility plot from a few slides prior, so that you can see that actually when the neutron to proton ratio is most sensitive is when the neutrinos are going out of equilibrium. So again, what's important to realize here, any BSM model, all right, that would be changing neutrino decoupling is going to have an effect on the neutron to proton ratio and the abundances. And in general, or I should say that it is possible, obviously, to calculate what those abundance responses are to neutrino decoupling. You can map the neutrino decoupling results into each one of these little boxes that you see on this plot. But there's actually a complication here because neutrino decoupling changes the evolution of the temperature, and that changes the neutron to proton rates through the positron and electron distributions. So something to keep in mind for the future. So to summarize, I hope you have realized that, Dirac neutrinos are an interesting thing to look at in cosmology. We looked at the anomalous magnetic moments to populate those states, but you can look at any kind of process, right? And the thing here I think to keep in mind, right, is that there's 3 of these states, so you pick up that factor of 3 when you're looking at changes in N effective. As a result, stage 4 and other future CMB experiments will be able to place really strong constraints, okay, on the thermal contact of those Dirac neutrino inactive states below the electroweak transitions. And because these are neutrinos and they have masses, they're going to affect neutrino-free streaming at later times. So another interesting aspect of cosmology to look at. When it comes to spectral distortions of the cosmic neutrino background, we're still working on this generalized entropy approach to describe this system, that's out of equilibrium. These 3 parameters, are a function of time. They're also, different for each flavor, but nonetheless, right, the fact that there were only 3 parameters we thought was very interesting. And the abundances do respond linearly, right, to perturbations in these neutrino distributions. So there may be a way to try and back out what the distributions are, if the changes to the cosmological observables and parameters. And keep an eye out. This work is still in preparation. All right, thank you.
Thank you, Evan. And so if you have any questions, please raise your hand in the chat. I see some hands already. First, I see Sherwood. Please go ahead.
Thanks for the really interesting talk. I was curious about the magnetic moments. And what I usually see in compact objects, the magnetic moments is used in conjunction with a coherent magnetic field to transform spin. Are there limits on how strong a coherent magnetic field might be in the CMB, or is it just assumed 0 by homogeneity isotropy?
Well, isotropy gives you a 0 magnetic field. But that's not to say, Sherwood, right, that primordial magnetic fields aren't important. And there are certainly models, BSM models, right, which would give you a primordial magnetic fields, and people do put constraints on that. Now, that's one model, and then we have to introduce another model to give you an anomalous magnetic moment. So it's kind of playing 2 games at once, almost. So I don't know of any constraints from cosmology, all right, that joint constraints on magnetic moment and primordial magnetic fields, but it's something that probably could be done. I would think that the constraints wouldn't be that good is just by themselves.
Cool, thanks.
Next, I see Susan.
Yeah, so I wanted to follow up on the generalized entropy approach. I just wanted to ask, in regards to usual grand canonical ensemble, then I just have the chemical potential and the temperature, I guess, for each neutrino flavor. But the whole idea of introducing a new parameterization in terms of epsilon, well, I think I could reparameterize it that way, even if I only had typical chemical potential and temperature. Aren't I just reorganizing the structure of what I think alpha can be? And so I'm not quite understanding what, how to say, I can certainly see you may include new physics with this restructuring, but maybe this is just a more effective way of describing the parameters of ordinary, I guess, standard module cosmology. I was wondering if you could just say a little bit more about the segue from the usual grand canonical potential to this generalized entropy approach.
That's a good question, Susan. So really, what we're trying to do, all right, in this case is, is out of equilibrium. All right. So these Lagrange multipliers, right, that I have written up here, right, that's for, the number and the energy. All right. Those are well-defined quantities. When we do neutrino decoupling, okay, those are no longer, constraints, okay, on the system. The system can change its number and its energy. And there's possibly other ways, other constraints though, on that system that we're trying to capture, right? So when we write this thing here, 1 over 1 plus e to the alphas, and we expand this, right, into alpha 0, alpha 1, and alpha 2, alpha 0 and alpha 1 are no longer, okay, the Lagrange multipliers, right, on the constraint for number and energy. Okay, they might be similar to that, right, but they are no longer that. And this alpha 2, this is something different, okay? This is some other, probably some interplay, right, between neutrinos and the environment, the cosmological environment of the early universe, right, that's at play here, okay?
I mean,
So-
that's wonderful, but I'm gonna just put to you that I can consider the theoretical framework for decoupling and have the parameterization that you write down and not necessarily be required to introduce new light degrees of freedom. So that's why I'm wondering, in this framework, which seems to be very handy for discussing neutrino decoupling, how I would tell. I guess, because this alpha minus L equilibrium is just telling us how our analysis is non-equilibrium. But it doesn't intrinsically speak to a need for new light degrees of freedom. And I'm wondering how I could tell.
So I apologize, Susan. Alpha equilibrium in this case is just 0 plus epsilon. Okay, it's not a thermal equilibrium or chemical equilibrium description, right? Maybe it's a bad notation. Okay, it's really just supposed to just write out the distributions as 1 over e to the 1 over 1 plus e to the epsilon. Essentially, that's all that is, right? And what I want to show you, right, in this plot here, right, this is the 2-parameter fit. Okay, this is the grand canonical fit, and I think you can see that this is much worse, right, than what we use for the 3-parameter fit. So just introducing that alpha 2 epsilon squared vastly improves the fit. Does this address your question, or am I talking past you?
I guess it does. I mean, you're telling me that it's sufficient to rewrite this parameterization with T center mass and epsilon, and that would be equivalent to the grand canonical ensemble, and that I see an improvement when I go rather to this construction where I have epsilon squared.
Yes.
I guess it's trying
One
to
more
address
term in
that.
the expansion. There's a
Right.
vast improvement. I'm sorry, I don't have actually the slides that show the statistical description of this, but it's statistically significant.
So I guess but I'm very naive, maybe of me to say this, but I think we have 2 points. We want to know how to model neutrino decoupling because I think it's a thorny problem and in the history of N-effective to understand not only the digits, but past 3, but exactly how they come out. So I view this formalism as additive in that regard. However, I would like to know beyond just being able to fit data or fit abundances, how I'm going to tell that I need extra degrees of freedom to explain the data. So I'm still, how to say, maybe I have to wait for your paper, and if that's the answer, then so be it. But I'm going to say that I'm still slightly flummoxed on this point. But others have questions and.
Okay, Susan, I'm happy to talk to you about this more in the future, offline. I'm probably not doing a very good
So
job.
I think I expressed my point, and that's
You
enough.
did.
Thank you very much.
Okay.
Great, let's move on to a question from Julian.
Yeah, just quickly on that plot with the 2 parameter fit, in that case, alpha 1, sorry, is not evolving as 1/t, I guess. It's more complicated.
The 1 over TCM, so to speak, lives in epsilon. Epsilon is energy over TCM. We're just trying to use dimensionless quantities,
Yeah, sure.
right, in this expression. So the
Okay.
epsilon squared, right, that we have here.
Oh,
Okay,
it's
that's
1/t square. Okay.
yeah, right. There's more units involved, all right, in other
Okay.
parts.
And previously, when you talked about the magnetic moments and the variation of N-effective, so there was a plot where so yes, you showed that even for, it looks like for very small magnetic moments, you still have a delta N-effective of like 0.14, 15 almost. So this is non-standard model, or is it standard model?
This is standard model, right? This is basically, right, if you have decoupling way up here at the, above the 100 GeV scale, you have the entire standard model of particles, all right? Maybe they're not all massless, right? Okay, but you have everything in there. And so if you have a decoupling, okay, if those neutrinos decouple, right, when the entire standard model is present, then the change to N-effective from these Dirac neutrino states is a little bit under 0.15.
But
right?
because I mean, it's way larger than all the standard model change to N-effective from 3. I mean, the standard model, the other standard model stuff is 0.44.
Oh yeah, definitely.
So this is much larger. So this should be included in a standard calculation.
No, right? That standard calculation, okay, that is weak interaction physics, right? This here, right, we had to, I'm sorry, maybe I didn't answer your question correctly when you said standard model, right? What I meant is that the plasma, okay, of particles are all standard model particles, but the interactions that are keeping those inactive Dirac states in equilibrium with that plasma, that is some BSM kind of kind of operation, right? In our case, we did anomalous magnetic moments, but it could be whatever. If these Dirac neutrinos are in thermal contact, right, with the particle physics standard model suite of particles, then this is the change that you're going to get in N-effective.
Okay.
Oh, sorry, I think I was muted. Baron, please go ahead.
Hi, yeah, thank you for that talk. So I have a weird question. I'm not sure if, I'm thinking that you have this cosmic neutrino background, which has a certain magnetic moment. Now we're trying to detect this background. Can we detect it in any way from the magnetic moment? So I understand that if we're doing some kind of a direct interaction, that's going to be 0, but a collective effect due to this magnetic moment at late times, has anyone explored that, maybe due to either galactic magnetic fields or extragalactic magnetic fields or anything? I mean,
no, indeed, there is, the fact that if you have neutrinos propagating, right, through magnetic fields, either, galactic or extragalactic, you'll have some kind of spin precession, which Sherwood Richards was kind of, intimating when discussing compact objects. However, right, you have to still detect those neutrinos, and there has never been any direct detection of the cosmic neutrino background, right? That's a major goal, right, for the neutrino experimental community. So, looking for like spin precession, probably you need higher energy neutrinos and different kind of experiments, maybe looking at Ice Cube or something like that. I think people have done analyses of that, but I'm not all that familiar with it.
Thank you. I was thinking of energy loss, maybe stealing energy from the magnetic fields.
That's certainly a possibility, but again, I'm not familiar with it.
Okay, cool. Thank you.
Welcome.
I see another hand from Yang Bai. Please unmute yourself and go ahead.
Hi, very nice talk. I just still question about that plot when you have the magnetic field, which the delta ineffective, when you have the mu to be very tiny. So let me make sure. So you do have a standard model prediction, mu is 10 to minus 19, right? So what you are telling in this plot, when mu is even, for about the new physics, standard model prediction, mu is 10 to minus 19, you say there is a prediction for delta ineffective to be for sure observed by CMBS4. I don't think you are talking about that, right?
No.
Okay. So then for this plot, right? So for this plot, when the mu is decreasing, keep decreasing, then the question is when the delta ineffective will drop, right?
I'm sorry, can you repeat that? I couldn't hear you.
So if I keep decreasing mu on the left side, at some point the delta ineffective will drop.
Correct.
Will become smaller. What is that value of mu?
Oh, I wish I knew the answer to that question. I'd write that Nature paper immediately, right? You're pushing beyond the standard model. All right, above the standard model, essentially. That I can't draw this line any further, right? Because I don't know what particles, all right, are above whatever kind of symmetry breaking gave the standard model in the first place. You're pushing to a very high scale.
So wait a minute. So if I look at the right panel of this DT decoupling, not this plot, sorry, previous one, this one. Yeah, this is slide. I look at the right panel, right? So basically you are saying that when I decrease mu, and the decoupling temperature is very high, right?
Correct.
So, but still is basically I relate to my reheating temperature, maybe correlated to that. But if my reheating temperature is very, very high, the moment I have some non-zero mu, let's say 10 to minus 15 here, right? I still have the standard model plasma to be TeV, right? In this unit you have, I still have at least some standard model degrees of freedom there, right? Still I can predict something, right? Even though I don't have a complete degrees of freedom, maybe I have some new particle, but let me leave those new particles aside, right? I still should have predicted something, right? So I'm still confused.
I mean, we just don't know what those particles would be, all right, and like what the distributions would be, above the electroweak symmetry breaking scale. All right, this line that you see here, right, it should be dotted or dashed or something. It's an extrapolation, all right, because it's assuming standard model physics up to that TeV scale.
Okay, very good. Suppose I assume standard model is valid up to Gata scale, like 10 to 16 GeV, then you will predict something for the next slide or next slide for the delta ineffective, right?
Yeah, but that's the thing though. If it's only the standard model up to 10 to the 16, GeV or something, this is all you're going to get in N effective, right? Because you're not going to have any other kinds of particles, right? You only have the standard model particles. I mean, personally, I don't think you can go up that high. I think there's probably a lot of rich physics, all right, in between, the TeV scale and 10 to the 16 GeV or something. Right. But, once you get up into that scale, the way we calculated these cross sections, that's no longer going to be valid, right? This is all standard model, physics, right? Just using this vertex function here. But I mean, this is going to change, right? Above, electroweak symmetry breaking at the very least.
I kind of gradually know what you mean. So because you are saying that to provide a certain value of the magnetic moment, we need basically we're talking about some hard dimensional operator for the neutrino, right? So that means there are some intrinsic scale. Those intrinsic scale will feed back as additional degrees of freedom when you think about the thermoplasma, and that will change the calculation here. Maybe that's what you're.
I think that is what I'm saying. Yeah, that's
okay.
a good
way. Okay. Thank you.
Thank you.
Do we have any more questions for Evan? I don't see any more hands, so let's thank our speaker again. And thank you all for being here. I'd like to announce, usually we do a seminar every other week, but most likely we will have a special seminar next Tuesday at the regular time. So keep an eye out for that announcement.
Thanks, Evan.
Thank you.
Thanks,
Bye-bye.
Evan.
Thank you.
Thank you.